Hey guys, welcome back. Figured it's time to go ahead and issue another lecture. We're going to be talking about surface water today. Surface water is a really cool subject to talk about because we deal with it all the time, right? The oceans, the rivers, the ponds. We're mainly going to be dealing with rivers in this conversation. Rivers are everywhere in the world. They're in Hawaii. They're on almost all the major islands of the Pacific, in Japan, all across Asia, and of course the famous African and South American rivers such as the Amazon and the Nile rivers as well. Will all be kind of discussed in some way in this lecture. So, with that said, let's go ahead and jump in. This is actually a picture here of the Mississippi River flowing through the northern part of the United States, not too far away from the Ohio River actually comes into it. Anyways, you get the idea that we see a nice flow of water. It's got some banks over here, some trees. This is kind of our idea of a nice serene river. But of course, not all rivers are like this. It turns out every river has its own unique personality, and we can actually characterize those personalities. So in order to understand how rivers, lakes, and ponds work, we need to understand how the water is distributed on Earth. So the total global water, it turns out, is 96.5% salt water. It's in the oceans. There's some of it is in saline lakes and groundwater. The groundwater is below our feet. And of course, the total global fresh water is only 2.5% of all the water. Okay, of that 2.5%, 68.6, about two-thirds, is in glaciers and ice sheets. About 30% is in groundwater beneath our feet. That'll, by the way, be the next lecture as we're going to talk about groundwater. And of course, fresh water is up here on top. That's about 1.3%. And then of that 1.3%, how's that distributed? Well, 73% of it is in snow and ice, 20% of it's in lakes, 3.5% is in soil moisture, 2.5% in swamps, and the rest, atmosphere, biological water, and rivers, kind of make up, if you add them all up, about something less than 1%. So we have the idea of how all of this fresh water is distributed. Now this is a figure that you guys might have some experience with since you guys were kids. It's the hydraulic cycle, or hydrologic cycle, I'm sorry. Basically, you have evaporation. The evaporation goes up into the evaporation of water. It goes up into the sky. You get precipitation. Basically, the raining out through either rain, snow, sleet, whatever, falling back down towards the land, usually in a liquid form, but sometimes in a solid form in snow. And then eventually that snow or melt or whatever it is will run off back into the oceans. And some of it will infiltrate down into the ground and actually form groundwater aquifers. So this is a process that is happening constantly. Now the amount or the sheer volume is immense, right? The amount of evaporation out of the oceans is 320,000 cubic kilometers of water. That's a lot of water. How much rains out? 284,000 cubic kilometers fall right back into the ocean. But some of it actually makes its way well inland. Okay, we also have evaporation, incidentally, off the land itself. So we got evaporation off the ocean, off the land. And so on the land, we get about 96,000 cubic kilometers of water that's raining down on all the rocks all over the planet. And then about 36,000 cubic kilometers of it goes off as runoff. The rest of it actually infiltrates in. So we're going to be talking about that runoff aspect. So the difference between runoff and infiltration depends on several factors: the intensity and duration of the rainfall, the amount of water already in the soil, the type of soil, of course, right? Water is more likely to run off on clay than it is in sand. It's more likely to soak into sand. The slope of the land is also really important. A really steep slope, you're more likely to get runoff than you are to get infiltration. And of course, the nature of vegetative cover. If you have a lot of grass, it's more likely to infiltrate than if you have just nothing but dirt, open fields. And here we can actually see kind of a combination of this. Here's basically an open field with little sprigs of agricultural products out there, and you can see it's not really holding the water back. It's running off pretty forcefully. And in effect, it's actually damaging the field. So runoff will usually start as something called sheet flow. And so here we see sheet flow on a road. Sheet flow develops into tiny channels called rills. And so we see these little, so here we have the sheet flow on this road down here. These little rills start to form as they run into what is eventually going to become a kind of a channel or a gully. Now this gully is something that we call a gutter, right? But our gutters are actually engineered gullies, is what they are. So gullies join to form brooks, creeks, or streams. Here's actually another place where this is happening. We have little rills of water that are focusing all of this towards the central gully, and then basically it's all taking this water right down this gully away from us here. A stream is any water that flows in a channel regardless of size. So by definition, this is actually a stream. This is also a stream. Okay, a river carries a substantial amount of water and has many tributaries. We're going to be talking about the architecture of rivers here in a couple of slides. Where does water go when it falls, right? Does it just simply go, where does it want to go? What's the ultimate destination for all this stuff, right? So water is falling here, but where does it eventually wind up? Well, if it's going to be in the surface, it's going to eventually try to make its way to the ocean. And so this idea of a continental divide sets in. So a continental divide splits a continent into two drainage basins. So here we see the continental divide in the western United States. It goes basically through the Rockies and up into the into the Canadian Rockies. Basically, any water that falls here on this side where I have my cursor is going to wind up somehow along some river, whether it be the Snake River or some other river, in the Pacific Ocean. If it winds up on this side, it'll wind up into the Missouri or the Platte River and eventually into the Mississippi River and out to the Gulf of Mexico. So this is basically what this sign is saying, is there's a pass somewhere along the continental divide here. And at this pass, every drop of water that falls on this side of the sign goes to the Atlantic Ocean, but every drop that falls on this side of the sign goes to the Pacific Ocean. So that's what this is basically stating here. And of course, the divides are usually at passes. Makes sense. It's going to be at the top of the mountain. It's going to go down the slopes of that mountain. All right. So now we can actually talk about smaller features. We talked about the continental divide. Smaller features are usually divided into things called watersheds, which are basically mini drainage basins. Basically, a drainage basin or a watershed is where streams drain an area of land called a drainage basin. So here we have kind of the upper edge of this hill, and every drop of water that falls in here winds up going down to the bottom of this little basin and eventually out to the mouth. The imaginary line separating one basin from another is called a divide, right? Just like the continental divide. Sometimes visible as a high ridge in a mountainous region, right? So the high ridge is usually the divide that we're looking for that separates the direction that water goes. But it's sometimes hard to see when you're dealing with subdued topography, rolling hills. It takes a little bit of surveying to figure it out, and sometimes the water goes in places you don't completely expect. But that's what science is all about, is figuring out those types of things. Rivers drain much of the land area. So this is basically how we get our drainage basins water out to some zone called a mouth. Exceptions are extremely arid or polar regions. Actually, polar regions are actually also very arid. They're basically, Antarctica is basically a desert. Even though it has a lot of snow, it actually gets very low amounts of precipitation. And basically it mimics the amount of precipitation you see in the major deserts of the world. So anyways, climate differences and human interventions influence the character of a river. This is absolutely true. At the end of this lecture, we'll actually be covering how that happens. River systems can be divided into three zones. So you have the headwaters, which is basically where the drainage basin is. This is the source of all of the rivers. So here we have the headwaters. This is the head of the drainage basin. And in this place, this is where we get sediment production occurring. So we get lots of erosion of these mountains, right? And then we get sediment transport through a central zone in something called a trunk stream. The trunk stream basically directs all the sediment across here. It's not depositing anything, but it's also not eroding anything. It's neutral. And then once it gets to the end of the river, it'll actually deposit it into a river mouth. Usually that river mouth is emptying into a pond or maybe even into a bigger river, or in the case of major rivers like the Nile and the Mississippi, they wind up in deltas, river deltas. And that would be a zone of sediment deposition. So sediment production, that zone, that very first zone, right up here, is where most of the sediment is derived. It's located in the headwater region or of a river system. The sediment is generated by bedrock broken into smaller pieces, bank erosion, scouring of the channel bed. So all of these different processes, we've actually talked about these in our discussion of sedimentary rocks and the origins of sedimentary rocks, talking about weathering. We talked about a lot of this stuff. Sediment is transported in trunk streams. In fact, here's a trunk stream right here. In balance, the amount of sediment being eroded equals the amount of sediment being deposited. So the amount of sediment coming into the trunk stream is usually about the amount that you find coming out the other side. In fact, we can actually see that this trunk stream is kind of a dirty water. It's kind of this milky brown color. And that's because it has little bits and particles of rock being transported within it. Silt, sand, clay, probably mostly silt and sand, being transported in that trunk river. And of course, eventually, sediment deposition is where a river reaches a large body of water. The energy decreases and the river deposits the sediments. Typically, only fine sediments are deposited in the open ocean. You need a lot of energy to be able to move larger particles. We're going to talk about that. But once you get into the open ocean, the velocity of the water is actually very, very low. And so as a consequence, it can't hold large particles, and rivers wind up dumping sand and silt right at the mouth, but the fines, I mean the silts and the clays, I should say, usually don't get deposited until you're way out into the open ocean. So when we look at maps on rivers, we can actually put together that certain rivers have drainage patterns. And these patterns are really useful for working out tectonic questions, for working out environmental questions, all kinds of things. So with that said, let's go ahead and cover these things. Drainage systems are patterns of the interconnected network of streams in an area. So it's dendritic. So dendritic is this pattern. This is basically like a leaf, like the veins in a, I don't know, like a maple leaf. And as a matter of fact, those types of veins are called dendritic veins. You also get radial drainage patterns. And so this is pretty common off mountains, especially volcanoes, cinder cones or domes, right? The water basically goes off in a radial direction, like spokes on a wheel. And this is what it looks like in map view. The rectangular, this develops usually along rock or beds that are busted up by faulting. And of course, trellis patterns, you can imagine, these are usually where you get zones of alternating rock layers that are really, really resistant. The consequence of this strong resistance is the river has a hard time cutting across it, so it'll run along it and then cut across it at opportune moments. So you get a pattern that looks like this with small streams that feed into it from the sides. So that leads us into a whole discussion on stream flow, how actually streams operate in river systems. So water moves in a river channel under the influence of gravity. This is not all that different than mass wasting. We're really just talking about mass wasting of water. And that's basically what a stream is. Water slowly flowing in a nearly straight path is called laminar flow. So when we look out here in this river, we see two kinds of flow. The flow back here is actually coming in a straight path. It's pretty smooth. That's laminar flow. So when we look over here, we find something very different. The water is moving quickly in an erratic fashion. Both horizontal and vertical movement is called turbulent flow. So here's turbulent flow, basically where we have the rapids, and then up here we have laminar flow. Nice, flat river surface. So another parameter we really need to focus on is flow velocity as well. And that is dependent upon a couple of important factors. One of them is the slope or gradient of the stream. So a steeper gradient has more gravitational energy to drive the channel flow, right? You have a higher angle, it's going to go faster. Channel shape, the wetted perimeter is the area where the river is in contact with the channel. So here we actually see a channel. The wetted perimeter is just basically the zone that it's touching the water. The most efficient channel has a small wetted perimeter compared to its cross-sectional area. Right? So we can look at this here. This is going to be, have a wetted perimeter here, and so we could say, what is going to be the perimeter? Well, this is going to be 1 plus 10 plus another 1. But down here we see 2 plus 5 plus 2. This is 9. So of these two, which one is going to have the smaller wetted perimeter? Obviously, it's going to be this one down here. So this one should be more efficient. And in fact, it is. Our observations show that the maximum velocity in this channel is much higher than it is in this channel up above. A narrow, deep channel has a small wetted perimeter, less frictional drag, and will flow more efficiently. So deep rivers flow fast relative to shallow rivers for this reason. So here we actually see these two kinds of rivers right here. Here we see a laminar flow, and here we see a turbulent flow. But what's actually generating the turbulence versus the laminar flow in these situations? Well, it turns out it's the channel size and the roughness. Now we know that the channel size is important, right? An increase in channel size will increase the cross-sectional area to the wetted perimeter ratio, thus increasing channel efficiency. That's what we just described on the previous screen, or the previous image. But rough channels, such as boulders, can create turbulence and decrease velocity, right? So this is basically the roughness aspect. So large rivers flow faster, but if you look at the two of them, this one looks more violent, but this one's probably actually having a higher velocity of flow. This is actually the Nile River right down here. So the Nile River is probably actually flowing faster than this river right over here. This river here is turbulent. It's got a rough channel with lots of boulders obstructing the flow. It does have a greater gradient, right? It has a greater angle. So it would be kind of interesting to go and measure them. But nonetheless, if we were to go out here and measure the water speed in the middle of this river, it's probably faster. Another parameter we need to be aware of is stream flow. So stream flow is basically the amount of water that's flowing in the river. Something we call discharge. So discharge is the volume of water flowing past a certain point in a given unit of time. So that's what these people here, these are actually University of Oregon students that are out in the middle of a river, and they're measuring how much water is going past their point. When discharge increases, the width, depth, and flow velocity increase predictably, right? Obviously, if you're going to put more water in, this channel is going to get deeper. And if it gets deeper, it gets a better ratio on its wetted perimeter relative to its size, and therefore the flow velocity increases. So that's what happens. When rivers get bigger, they get faster. And by the way, if you're ever interested in doing any type of research on rivers, the stream flow is well understood and well measured across the United States, in all 50 states. So the United States Geological Survey measures flow velocity, discharge, and river stage, which is the height of the water surface relative to a fixed point. So you can put a gauge in here and you can see if the river's at 3 feet depth or at 10 feet depth, depending on what's going on. You can see these trees down here knocked down. That would have been knocked down by a flood at some point in the past. So the water at some point got quite high. These data are useful for resource management, and the data are publicly available. You can go on to the USGS website and you can download as much stream flow data as you want on almost every river. Okay, it's publicly available. There's a lot of downstream changes that occur. You know, we talked about what it looks like in the headwaters, but we didn't necessarily talk about what that profile looked like in terms of its elevation. We kind of implied it. So a longitudinal profile is a cross-sectional view of a stream. So this would be a longitudinal profile of a place called the Bouquet River Profile, or Bouquet River, which is drains into Lake Champlain, if I can remember. So the head or the headwater is the source of the stream. So here we see the headwaters here, a place called Dease Mountain, which would be located over in this zone here. The mouth is the downstream point where the stream empties into a larger body of water. So down here's the mouth at Lake Champlain. Most longitudinal profiles have a concave shape. So notice this nice concavity right here. That's a concave shape. You actually wouldn't expect it to have a convex shape. That would be kind of weird. Discharge increases towards the mouth. So the water here is actually a small trickle compared to the amount of water that comes out at the mouth here. And we can see the reason why. Look at all these tributaries that are adding into the main stem of the stream as it comes into finally the lake. And the channel size and velocity also increase towards the mouth. So the water is actually moving fairly slow through here relative to what it's doing down over here right before it enters the mouth. There's a couple of, you can see waterfalls on this river. But for the most part, this is kind of the where most of the erosion is occurring. You can tell by the slope. And notice that this over here is pretty flat. So the amount of erosion actually decreases as we go down through here until we finally get to the mouth at Lake Champlain, where, of course, erosion finally stops. So to kind of bring us back to this old image, we have the headwaters here. Here's our trunk stream, and here's our mouth. What happens as we go across this system? Well, at the headwaters, we have a flow velocity that starts to increase until it reaches the mouth. So this is the position at the mouth. This is the position at the headwaters. Flow velocity starts to increase. The channel slope gradient actually decreases, right? Just like we were seeing over here. You see this relationship here. It's the concave shape. The channel roughness also usually is pretty rough up here, but it actually smooths out as we get further downstream. And of course, the amount of discharge and channel size predictably get larger as you go downstream. So there's a lot of different things that we start to experience when we look at rivers in detail, what they actually do to the rocks, what they actually do to the environments that they travel through. So the erosion related to slope, discharge, and bed bank sediments is massive. There's sand-sized particles that are easily eroded along the rivers. Silt and clay-sized particles and gravels, it turns out, are a little harder. Silt and clay turns out to have some level of cohesiveness. Clay likes to stick to itself. Sand doesn't do that, so sand is easy to transport. Gravels are just large and massive and are relatively hard to move. Channels with cohesive, silty bottoms are typically narrower than sandy channels. It's just an observation that's made. Quarrying, which means the removing of large blocks, involves removing large blocks from the channel bed. So, that's something that rivers do, is they're moving these large blocks, especially at flood stage or during mud flows. They transport large blocks of material from the channel bed, and that has a dramatic effect on how rivers transport material downstream. It's the reason why you find sand in New Orleans that actually originated in Minnesota. It's because of the ability of these rivers to transport large amounts of material, large blocks, and breaking them up. They tend, by scraping, this is the way that they do erosion. By scraping, bumping, and rubbing, abrasion both erodes sediments and polishes them. And one of the classic ways this happens are these things called potholes. So potholes form when fast-moving, swirling sediment eddies abrades a hole. So you see these blocks in here. This water during flood stage will come in, it'll fill this in, you get a nice eddy going. But these blocks that are in here, these little cobbles or sand grains or whatever's in there at the time, will start to swirl around with it. And basically it just works its way down into the rock and produces this nice round pothole that forms. And by the way, these form on coastlines as well, especially areas where there's nice soft rock like Hawaii, where there's a lot of basalt. Basalt's a fairly soft rock, and you find a lot of potholes on the coast. Rivers are also really good at corroding things. So corrosion, rocks gradually dissolving in the flowing water, can all occur in limestone, bedrock channels. It can actually occur in any kind of channel. The pH of most river water is about 5.5, which is acidic. So it tends to corrode things and wash them away once it's corroded. So how is it that the rivers move stuff? That's what this slide is all about. This is the transport of sediment by streams. So all streams transport sediment, all of them. There's never been an exception. They do it in three ways. The dissolved load, which is in solution, so basically it corrodes things and it dissolves it, so this is an invisible thing. The suspended load, which is in suspension, it's floating around. That's usually the silts and the clays. It's actually floating around in the water. And of course the bed load has two different types. There's the saltating or bouncing rocks. You'll actually find things saltating. You'll find things sliding. And you also find things rolling. Boulders and sand and gravel tend to do these types of things. Boulders are especially good at rolling. Gravel and cobbles usually like to slide. Sand will saltate or bounce along. Most of the dissolved load is brought to a stream via groundwater. Not all of it is necessarily right along the banks of the river. As a matter of fact, very little of it is. The dissolved load is not affected by stream velocity, it turns out, in any way, shape, or form. It's completely chemical. Dissolved minerals precipitate when water chemistry changes. So, I can't really show you what that looks like, so just know that there are entire classes, very interesting, that deal with the chemistry of natural waters or the geochemistry of natural waters. And people make a very nice living monitoring how healthy ecosystems are by studying the geochemistry of natural water systems, especially rivers and lakes. The largest part of a stream load is carried in suspension, however, and that's mostly our silts and our clays. And when we look at this river here, we can actually see that there's a suspension right here, and there's a suspension right there. And the reason why there's suspension here and here is because, well, that's where the river's going the fastest. We'll be describing that here shortly. Over here, the river's actually going slightly slower. And so we actually see there's a relationship, it turns out, between the sediment distribution and the velocity of the river. And here's, as a matter of fact, speak of the devil, here it is. Amount of material carried in suspension is controlled by stream velocity and settling velocity of sediments. Settling velocity is the speed at which a particle falls through a still liquid. So here we have particle grain size. This is usually given in millimeters, so the very small stuff is clay, silt, sand, a lot of coarse material over here. And here's the stream flow velocity in centimeters per second. So 100 centimeters per second, that's a meter per second. That's a little, 3.3 feet per second of motion. So at 1 meter, we can expect that water can start picking up things that are coarse material at about 20 millimeters, okay, or whatever this represents. Oh, it's a logarithmic scale. So yeah, it's about 20. You get the idea. If it was going at 5 centimeters per second, which is pretty slow actually, right here, it'll actually start picking up sand. If it's going even slower than that, a half a centimeter per second, it'll be picking up silt, largely large silt. And clay, of course, notice it's all the way over here. Clay is always picked up by water. So that means that we can go ahead and start describing bed loads, right? We've kind of gone over how things get suspended, but bed loads are important. Coarse sands, gravels, and boulders move along the stream bed by saltation, which is skipping or jumping, less rapid and more localized than transport via suspended load. You can imagine here, this is a river that is not flowing at its full capacity right now. These things are obviously not moving around or saltating around. That's because the river's at a low stage. If it was at a higher stage, those rocks would be moving like crazy. And trust me, you wouldn't want to be caught in such an event. It would be quite frightening to have these rocks rolling around at your feet while you're trying to walk around the stream. As a matter of fact, here's kind of another river. This is going a little faster. You notice that in the middle of the river we have large boulders, but over here we don't. This is because the water is able to move stuff, but here it can't. Capacity is the maximum load of solid particles a stream can carry. So the greater the discharge, the greater the capacity. Competence is the maximum particle size a stream can transport. So streams with a faster velocity have a higher competence, right? Deposition of sediment by a stream. There's all kinds of different ways this can happen, but deposition occurs when a stream's velocity is less than settling velocity. So remember this. If we have a stream that is going at a very high velocity, let's say, let's say a meter, 100 centimeters per second, right here. That means it's moving everything from coarse material, sand, silt, and clay. And if it moves into an area of quieter water, let's say it moves into 1 centimeter per second, that means that everything larger than sand, right? Everything from sand this size and over is going to settle out, because if we go over here, we look at 1, drops down. And so only it carries clay, silt, and fine sand. The coarse sand and the coarse materials all settle out when it slows down. Go back to where we were. And so here we can actually see, a stream that's moving through, large boulders everywhere. So this is a stream that when it really gets going can move boulders. Right now it's not doing that. So it's deposited the boulders in the stream, at the base of the stream, or at the bed of the stream, I should say. Particles of the same size are deposited at the same time in a process called sorting. We've talked about sorting before, so you want to make sure that you go back to the sedimentary lectures that we gave towards the beginning of class that deal with the issues of sorting. But basically larger particles, by virtue of the slower water, fall out first. And so we get entire zones of nothing but boulders, just like what we see right here. This is all boulders. There might be some smaller boulders in here, but for the most part, there's no silt, sand, or clay. This is all boulders, it's rock. And sediment deposited by streams are called alluvium. So here we actually see a river that comes in. It starts to slow down as it comes out of the valley, and it leaves a whole bunch of boulders here. This is a big alluvial valley right here. Not really the safest place to build a house, because as you can imagine, a major flood would come in, strip up all of the material, and deposit it right over your house. So this is kind of a neat area here. several different kinds of channels that we need to bring up, actually two in particular. The main one that we're going to be talking about is bedrock channels. Well, we're going to be talking about both of them actually quite a bit. So the bedrock channels are cut into the underlying strata. So in other words, the water is touching the bedrock. These typically form in the headwater region where streams have a steep slope. Potholes, remember we talked about potholes, steps, or you can even think of waterfalls, and pools are common features of bedrock channels. So this is a bedrock channel coming down. You can see there's a nice, probably this is a slate or a siltstone that's underneath it, and it basically runs right across the solid raw rock, right? Channel pattern is controlled by the underlying geology, as we've talked about the channel patterns at the beginning of this lecture. In contrast are alluvial channels. So alluvial channels form in sediment previously deposited in the valley. So it's not on the rock, it's not on the bedrock anymore. And these are typically associated with a floodplain. So channels can change shape as materials eroded and transported, and we actually see this as happening right here. Here we see a stream that comes together, it separates, and then it comes back together. This is called a braided stream. We'll be talking about braided streams in detail a little shortly. But we'll notice that occasionally the stream exceeds, it actually gets too large, it exceeds, and actually here's something called a cut bank over here. So occasionally this gets underwater as well, and it gets eroded away, and the stream goes right along the edge here as well. Constantly moving around. It's not controlled by the bedrock, it's controlled by the loose sediment at the surface. And alluvial channels result in some amazing things. One of the most amazing things that we see coming out of these things are, well let's talk about it. Basically meandering channels. These are streams, because streams transport suspended sediment in broad sweeping bends. It tends to meander around. It tends to move around. So we were talking about how this moves around from time to time, and you can even see the cut bank over here. It's doing the same thing here. So here we see a stream that comes in, it's moving this way, this way, this way, this way. But at one point it actually was way close in here, and it was actually straighter, and it cut over here like so. It's meandering, it's moving around, it's not going in a nice flat, straight direction. The outside of the meander, which is called the cut bank, is a zone of active erosion. So here we see a meander going around this bank here, and so all the erosion is actually happening here, right at the edge. The inside of a meander is a zone of deposition, and the reason why is because the zone out here is moving actually at very high velocity, but the zone inside is actually going fairly slow. So here we see erosion, and here we see deposition, and so originally this river was probably running like right through here. Now it's back here, and it's deposited this entire bank all the way behind it. Through time, the bends in a channel can also migrate and eventually join together, right? So this is kind of what's happened here. This was originally a situation where the meander came through. This river actually went this direction. And you can actually see part of the old river right over here. And it connects, used to connect like this, looped in. And over time, that cut bank that originally went this way cut so far that it basically caught the other side of the river, and it cut off this part of the river and left it into basically a lake unto its own. And this kind of lake is called an oxbow lake, and they're really common all over the world, especially in trunk streams. This is a real common phenomenon. So a meander that is cut off from joined bends is called a cut-off oxbow lake. And you see that in alluvial channels. You do see that also in bedrock channels to some extent, but not as prevalent. Braided channels. A braided channel is a network of converging and diverging channels that thread among numerous islands or gravel bars. So if you were out here, you wouldn't want to necessarily build a house out here because you never know when these little streams are going to separate and recongregate right at your feet. A large portion of the load is coarse material. There's a lot of coarse material in here. Bank material is easily eroded and reworked. All right, this is really loose stuff. It's constantly moving around, even season to season, even within the year. It might shift around in all different directions and rework that sediment. So to create stream valleys, a lot of things kind of go into this. First off, we know that there's a zone of erosion, a zone of transport, and a zone of deposition. But what is the ultimate how would I say it, a kind of goal of a river. What does a river want to do? I hate to use those kinds of phrases because rivers don't really want to do anything. They just do what they do for physical reasons. There's just laws of physics that are making these things happen. But ultimately, what is going to happen? What is the end result of a river that gets to do all of its things unimpeded? So what is driving this is something called base level. Base level in graded streams. The base level is the lowest part to which a stream can erode. Basically, a stream can erode down everything flat until it reaches its base level. And in most places, the base level is the ocean, right? The Mississippi River is eroding everything and trying to bring everything down to sea level if it can. As a matter of fact, that's what it says here. Ultimate base level is sea level. Local or temporary base levels include lakes, right? So you can build a lake that changes that on a local level. Resistant layers of rock and large rivers. Changing conditions causes readjustment of stream activities. So imagine there's an earthquake or you build a dam. So in this case, we'll build a dam. That's what's happening here. Here we have a river. Here's the base level, right? So profile of stream adjusted to base level. Here's that base level right here. And the river's basically trying to knock this hillside down. But if I go and I build a reservoir, there's a new base level here. And so what happens? Well, it means that it stops eroding this area here at the reservoir and instead starts depositing stuff because here's the new base level, right? And so here's the original profile, and what is on top of it? New stream profile formed by deposition of sediment. So there's a depositional wedge that is actually formed right here by the stream coming in. And so most reservoirs, as a matter of fact, every reservoir I can even think of that has an active stream coming into it has deposition occurring where that stream comes in. And so once in a while, the dam has to, the river has to be, or the reservoir has to be drained and the dam cleared out of all of the sediment that piles into the lake, and then it can be refilled again. Some lakes happen very often and some not so often. Raising base level causes deposition. So that's what we see here. Lowering base level causes erosion. So if I was to lower the base level, it would actually dig in even deeper. So you can lower that by actually doing, well, there's a couple things you can do. We're going to talk about that here. So base level and graded streams, we're still talking about that. Changing conditions causes readjustment of stream activities. Raising the base level causes deposition. All right, so this is where we're at here. Lowering base level causes erosion. A graded stream only transports sediment. No net erosion or deposition of sediment. So what we're seeing here is, here's another graded stream prior to faulting. We have an earthquake, and it lifts this whole thing up. Now the graded stream was actually pretty happy eroding this nice flat surface, but this has actually put a kink. There's a nice waterfall and a nick point that is generated by the earthquake. Nice resistant bed that's holding everything up. And so what happens over time is basically the river is trying to re-accomplish its base level, right? So here's the base level. The fault lifts up that base level, and the river immediately starts to erode that base level back. And over time, look at this. The fault winds up being almost completely unseeable over time. So this ultimately will be the new profile after the river is done doing its erosive activities, just like we saw up here. Except in this case, it's now faulted at the tip, whereas over here it wasn't. There's all kinds of different consequences for this. So one of the things, if you wind up doing uplift, like on these faults, you wind up getting a steepening or a deepening of valleys. So steep gradient and channel far above base level leads to downcutting of the channel, right? So when we're looking over here, we basically uplifted all this block and it started downcutting. It actually started digging in a valley right here at the waterfalls, and the waterfalls started moving backwards. In this case, this is the Yellowstone River, and the Yellowstone River is clearly cutting down into this rock, and this is because it's in the Rocky Mountains. The Rocky Mountains are an actively uplifting river, a mountain system, and the rivers are trying to cut back down to base level and maintain that old base level if they can. In this case, it's digging down as deeply as it possibly can, and the reason why is because the Rocky Mountains are actually rising faster than the rivers are able to cut down through them. V-shaped valleys with steep sides are the result of severe downcutting. Rapids and waterfalls are prominent features in V-shaped valleys. So here we see a beautiful waterfall on this end, and it's common in regions undergoing tectonic uplift, such as the Rocky Mountains. Okay, now that you have that kind of understanding of what base level is, you should be able to look at the Grand Canyon and realize exactly what is happening here. The base level of the Colorado River, which is down here at the bottom, is much lower than the rocks. So as a consequence, the river, which is trying to maintain its base level, is in an area where the land is actually uplifting straight up. Tectonic uplift is basically pushing everything up. As a matter of fact, the top of the Grand Canyon is about a mile taller than the base level of the Colorado River. In fact, the Colorado River is still actively trying to get down to an even lower base level. So it's fascinating. The geology of the Grand Canyon is amazing. It's a place that you should definitely visit in your lifetime. Okay, so we've talked about how downcutting occurs and we get lots of erosion, but we haven't really talked about where it goes. And basically, it winds up in deltas. Deltas are areas of active deposition from sediment-filled streams. So deltas form when sediment-filled streams enter a large body of water. This, for example, is a delta. We see all the streams coming in and actually distributing sediment all along here. And this is the Salange River that dumps into Lake Baikal, which is in Siberia. The stream's forward velocity decreases, lowering its carrying capacity. Remember, it's got a bunch of silt, sand, clay, probably some boulders or some gravels from time to time in it. If the velocity of the river is reduced, it can't hold the larger materials and it settles out. So size of sediment varies in the delta. Coarse sediments are deposited close to the river mouth. So here's the river mouth here, so we get a lot of coarse material here. Whereas fine sediments are deposited at the outer edge of the delta, so maybe right along the coast, right out here, we get the finer stuff. The main channel divides into several smaller channels in the delta called distributaries. So here's the main river, the Salange River, but you can see that the water is being distributed around almost the same way that a braided stream would do the same thing. But you don't necessarily have to always have a delta that dumps into the ocean. Sometimes you can just have a delta or a river or alluvial channel that dumps right out into land. And that produces something called an alluvial fan. So alluvial fans are fan-shaped deposits of sediments at the base of mountain fronts. So here we see a stream that came in, is taking all this stuff out, but as soon as it hits the bottom of the valley, it loses its velocity, and the water, in this case, is Death Valley. The water actually evaporates. It doesn't go very far. So there's no water to move it anymore, and it just piles up down here. The stream emerges onto a flat lowland, the gradient drops, and the sediment is deposited. So you get the idea. In this case, you can't even see the stream, but there is actually one probably buried within the alluvium. It's basically a groundwater stream at this point. Because it's Death Valley, there's a lot of tourists. This is actually a road that goes around this alluvial fan right here. All right, with that said, I hope you kind of enjoyed this discussion on streams and rivers and valleys. I know there's kind of a lot of information. I hope it wasn't too confusing, and I hope I didn't go through it too fast. I really wanted to make sure that this video was brief for you. But if you have any questions, by all means, send me an email, meet me on the discussion boards, or just find me in my office hour. In the meantime, have a good one. Talk to you soon.